always limited by the constraints of our ability to make measurements. Always. Okay, so that's why I'm making it an attempt to apply single sense. There's another reason why this current needs to be small, by the way. If you read your galvanometer, what is the scale of your galvanometer? Some of them are different than others, but they're going to be one of two different things. They're going to say millivolts, which is because originally, not now, but originally they were set up as a simple voltmeter to begin with. Or, if it's a pure galvanometer, one that is designed as a galvanometer properly, it will measure current. Here's the thing about these things. I think I wrote it in the lab. It turns out that this little movement arm is physically limited. It saturates with a certain maximum current. I think it's about 5 milliamps or something like that. I think I wrote it in the lab. There's a maximum amount of current that will physically flow through this thing before the needle pegs. It has nothing to do with voltage, just the needle will peg. So the other consideration is that this can only have whatever that maximum physical current flow through it in order to be a useful measuring device. If you got a bathroom scale and it only measures up to 200 pounds, you ain't going to measure 350 on it. It's going to saturate. The same as this. So we have to set up that resistance so that when you're measuring the maximum voltage that you're trying to measure, you won't overshoot your needle, your signal. So we're limited by the amount of current this thing can flow. So that's the other reason why we need to keep this IM small. So there's multiple reasons here. So let's think about this for a second. We've got a 12-volt battery. Let's make it 5 volts. If our power supply is 5 volts, so if the original V is 5 volts, then whatever the resistance of R1 and R2 are, you're never going to have more than 5 volts of electric potential across any of these elements. The sum of whatever the voltage is across R1 and the voltage across R2 will add up to 5 volts. So a nice place to start might be to say, well, how could we design this meter so that it could measure maybe a maximum of 5 volts? That way, if I wanted to measure the whole voltage across the circuit, I'd be able to measure it by looking at the maximum value of my scale, or any proportional value smaller than that. So how might we do that? If 5 volts is what we want to maximize our signal. And by the way, here's a terminology. I'm always really loose with terminology because I don't want to lose meaning by hiding behind language. But when you have a scale that will saturate at a certain value, we call that maximum scale value the full scale deflection. Now in a digital sense, nothing deflects. But in a gauge sense, where you have a moving needle, when it reaches its full deflection, that's the saturating point for the scale, so we say it's the full scale deflection. So essentially what we want to do is we want to set the full scale deflection so that it will happen when you have 5 volts. So if this is our need, if this is the maximum reading we want, then we would want to set the current in the meter to be maximal. I'm going to say IM max. If it's 0.5 milliamps, or whatever it is, read it, tell me what it is in the thing, I forget. I just, 5 milliamps, I'm going to assume it's 5 milliamps. I don't know if it's more or less, I just don't remember. So in this case, it's maybe 5 times 10 to the negative third amperes. Okay? So what voltage, or I'm sorry, what resistance here, if we assume that the resistance across this little movement arm is tiny, and it's so tiny, it's immeasurably small, what resistance would RM need to be so that you only have 5 milliamps when you have 5 volts? We would want RM then to be 5 volts divided by 5 times 10 to the negative 3 amperes, or 1,000 volts per ampere. And that unit we call the ohm. So in other words, if I put 1,000 ohm resistance here, then if this voltage were 5 volts, I'd max out my scale. Anything less than that, my scale will be something smaller inside there, as read by your scale. Okay, so that's the easy part. Now comes the calibration part. These meters do not measure in voltages. They don't arbitrarily measure 5 volts. We picked that. We could have picked 10 volts. We could have picked 0.5 volts. We could have picked any number to maximize our scale reading. That's what we do with our multimeters. So we have to establish on our scale, on our galvanometer, what corresponds to 5 volts. So you look at the maximum reading on your galvanometer. That maximum reading, say 5 milliamps, that reading corresponds to 5 volts. Half of that reading, 2.5 milliamps, would then correspond to 2.5 volts. And it should be proportional everywhere from 0 to 5 volts, just by measuring the milliamps. Now, if we were a meter manufacturer, we would just replace that ammeter value, or that amp value, with the calibrated voltage. But we're not going to tear this thing apart and rewrite numbers in. We're going to make a calibration. So, in the end, then, the last part of the puzzle is to then calibrate the scale units to voltage. So if the maximum reading is 5 milliamps, then 5 milliamps would correspond to 5 volts. And then all the way down, 3 milliamps should correspond to 3 volts, etc. It's pretty straightforward, but I mean, that's essentially the idea. And that's what we do with pH meters in chemistry. Take a little pH meter, you stick it in that thing, whether it tells you what it is or not, it's measuring a voltage because it's measuring a current. And what does it do with that value? Well, you put in your standard. You say, well, when it's a pH 10 reference standard, you put that in there and you tell it it's 10, so it knows it's 10. Then you go and you put in another reference sample 3 or pH 7, and you tell it that that's 3 or that's 7. Now it has a calibrated scale where it's measuring voltage or current, but it's telling you that it's a calibrated value corresponding to a certain pH. So we do this all the time, it's just normally it's all done behind the scenes, not in front of the scenes. So we're going to actually use it directly up front. So that's essentially the idea of the first part of the experiment. The second part is an extension of this that I'm not going to talk about right now because I want you to fully appreciate this part. And as you go into the second part, then I'll just discuss it individually. I want to stop talking now. But I hope I've added some value to what it is you're going to do today, because it's simple, subtle. You've seen all of these in most cases, but it really isn't. And it's important that you appreciate a couple of the sentences. It really is. So I'll let you guys take a break. Get set up what you need to get set up. I think everything is pretty accurate in the lab as far as what we need and we're going to do with it. I apologize for the verbosity of this little discussion, but I don't want you